Dear students, welcome to this lecture. After listening to this lecture, you will be able to explain the binary search tree and its operation. What is binary search tree? So already we know about that binary tree. In a tree, a node have at most two children means the tree is called binary tree. If a binary tree is ordered, then it is called like binary search tree. How it is added? If all the nodes in the left subtree have a value less than the root node. Correspondingly, all the other nodes in the right subtree have a value either equal to or greater than the root node. If condition is true, the tree is called binary search tree. This is simple binary search tree. In this tree, 39 is root node. The entire left subtree have less than values compared with root node 39. At the same time, right side of this tree is greater than 39, that is root node. So it is called like binary search tree. Not only root node, and each and every root node for their child, the condition will be applicable. If example, we will consider 29. This 29 is root of 28 and 36 node. So left side 28 is there, it is less than that 29, and right side 36 is there, it is greater than 29. So it is called binary search tree. Wherever we are searching in the node, a condition must be satisfied. For example, we have some values. With based on that values, how we can make binary search tree. In this example, first I take 45 values. Compared with this value, I will insert next value. So now I will take 39. 39 is less than the 45. So I insert 39 in the left side of the node. Next value is 56. When I compare with the 45, it is greater. So I added 56 in right side of that node. So next value is 12. Where we can add 12, first we can compare 45. Then we will go to left side. Then 39 is there. Again we will compare with 39. It is lesser. So we will go to left side of 39. So the 12 is inserted left side of the 39. What's the next value? 34. So first we can compare with 45. It is lesser. Then we will go to 39. When we are compared with 39, 34 is lesser. So I will go to left side of that node. Again, 12 is there. When we are compared with 12, 34 is greater. So I will go to right side of that node. So now I added 34 right side of 12. The next value is 78. How we can add 78? First we have to compare with root node 45. So 78 is greater. So we will go to right side. In right side again 56 is there. When we are compared with 56, it is greater. So we can add 78 right side of that node. So next value we can add where. So the next value is 32. When we are compared with the root 45, we will go to left side 39. Again we will compare with 39. It is lesser. Then we will go to left side of that node 12. Again we will compare with the 12. So it is greater. Then we will go to right side. Then 34 is there. When compared with 34, it is lesser. So we are insert 32 in left side of the 34 node. What's the next value? The next value we can add it as 10. Where we can add, so when we are compared with the root 45, then go to left 39, again go to left 12, again we will insert left side of the 12th node. So next value is 89. How we can insert the 89? Compared with the 45, then it will go to right side 56. Again compared with that, it is greater. Then we will go to right side. Again 78 is there. Again we will compared with 89. It is greater. Then we will add right side of that node. So 89 will be added right side of the 78 node. Next value is 54. How we can add the 54? Compared with the root node 45, it is greater. So we will go to right side. 56 is there. When we are compared with 56, it is lesser than that. Then we will add 54 left side of the 56 node. So now we are added 54 is left side of the 56 node. The next value is 67. How we can add it? So again, same procedure we have to follow. First, we will compare with 45. Then we will go to right side 56. Again, we are compared with that. It is greater. So we will go to right side. Then right side 78 is there. When we are compared with 78, it is lesser. So we can add left side of that node. So in left side, we can add 67. Finally, the last value is 81. How we can add the 81? Again, same procedure. 45. When we are compared with the 45, it is greater than 56. Then when we are compared with 56, it is greater. Again, we will go to 78. It is greater. Then we will go to right side 89. So 89 is lesser than that value. So we will add 81 as left side of that particular node. So the final binary search tree is like this. The step 12 is showing the entire binary search tree. In binary search tree, we will perform the following three operations: search an element, insert an element, delete an element. So already we have performed these three operations in linear data structure and as well as nonlinear data structure. What is search an element? Since the nodes in a binary search tree are added, the time needed to search an element in the tree is greatly reduced because we can search the element when compared with the root node. If it is lesser, only we can search left subtree. If it is greater, only we can search right subtree. So at every node, we get a hint regarding which subtree to search in. For example, in this binary search tree, in the binary search tree, we will search one element. For example, we will search 65 is there or not. Now we are search 65. How we can search 65? So first we will compare with root node. Root node is 50. So now when we are compared with 50, so 65 is greater. So now we will go to right side of that node. So right side, the value is 70 is there. So when we are compared with 70, the 65 is lesser. Then we will go to left side. So in left side, 60 is there. So when we are compared with 60, The 65 is greater, then we will go to right side. So the right side value is there. So like that, each and every node, we are getting the hint of where we will search. Like that, we can perform the search operations. This is algorithm for search operations. First, we can check if tree tends to data, that means root value, root node, equal to value, which value we are given, that is mapped with root value, or tree equal to null. So if any one condition it is true, return tree value. That means tree is null or tree is the data value, that is root value. That means there is no child nodes. Else means, so the particular tree have left subtree and right subtree. So then we will check with the value is lesser than tree data, that is root value. So the value is lesser than root, we can search the element from left subtree with a particular value. If else, that means it is not lesser than, it is maybe greater than. So we can search the element in the right side of the tree. So like that, we can perform the search operations. So here, the binary search tree I shown here. Now we will discuss with insert a new node in a binary search tree. How we can insert a new node? First, we have to apply search operation where we will insert a new node. Then, once we find the correct position, then we will insert the particular node on the particular location. We first find the correct position where the insertion has to be done and then add the node at that position, because insert function changes the structure of the tree. It may be the greater value or lesser value. Whatever it may be, we have to find the location of the particular node or value, then we can insert the element. So here I want to insert 33. How I will insert 33? So we have to check. So first we have to find the location where we have to insert. When we are compared with the root node, it is lesser. So the root value is 50. Our value is 33. When we are compared with 50, it is lesser. So we will go to left side. In left side, 30 is there. When we are compared with 30, 33 is greater value. So we can add 33 in right side of that node. So in right side, some other nodes are there. That nodes have value 40. When we are compared with the 40, it is lesser. Then we will go to left side of that particular node. So here 35 is there. In 35, when we are compared with 33, it is lesser. So we can add 33 is left side of that node. Initially, how to form the tree, I explained. The same procedure we can follow for insert and node in the binary search tree. It's a simple algorithm for insertion. In this algorithm, we can call the function insert with the tree comma value. Which value we can insert, that is val, that is value. Where we can insert this value, that particular tree, we will pass it here. First, we have to check the tree is null. That means tree is not there. We can create the new node because we are insert a node in the tree. If it is null, we can allocate the memory for the particular tree. Set tree data is a value. The value is assigned to tree data, and left side and right side pointers are null because there is no more nodes are there. It is the first node. When we are inserting the first node, we have to allocate the memory and we can set both the pointer is null. Else means some data are there. Then we have to check the value is lesser than the data or greater than the data. If it is lesser, we will go with the left side of the tree. And then else, if we will go to right side of the tree where the position is left, that is the less, then we can insert the value of the particular data. till insert the value, this function will work recursively. Now delete a node in binary search tree. How we can delete a node? The delete function deletes a node from the binary search tree. However, utmost care should be taken that the properties of the binary search tree are not violated. What is the property? The left subtree must be lesser than root node and right subtree equal or greater than the particular root node. That is the properties of the binary search tree. It should not be violated. And nodes are not lost in the process. When we are delete, no other node should be lost. For delete operation, we have three categories. First category, a node have no children. If the node have no children, that is one of the category. The another category is a node have one children. Then if the node have one children, we have to follow separate procedure. At the same time, if the node have two children, that is also separate category because we have separate procedure for doing these operations. So example, delete a node that has no children. If there is no children means no complicated procedure we have to follow. Simply, we can find the element is there or not. If it is there, we can remove it because there is no children. It's not affect the binary tree. So in this example, when we are compared with the 45, 78 is greater. Then I will go to next right side. 56 is there. When we are compared with 56, it is greater. Then I will go to next right position. The right position data is there. Simply I can delete the 78 and it's not affect the structure of the tree. It's not affect the properties of the tree. So there is no complex procedure for delete a node which has no children. In case a node have one children, what we will do? That we will discuss now. In this case, the node child is set as the child of the node's parent. So in case the parent node have different options. Here, if the node we want to delete, the particular child will be attached with the parent node. So that means replace the node with its child. So we will see in the diagram. So example, I want to delete 54 in the diagram. So first we have to apply the search operation. 54 is there or not. So for that, first we are check with the root node. Then it is greater. Then we will go to next node 56. Then it is lesser. Then it will go to left side. The particular node is there. Then in case we want to delete the 54, what we will do, the procedure is the child of the particular node will be attached with parent of the particular node. So the child of 54 is 55, then 55 will be attached with parent of 54, that is parent of 54 is 56. So directly the 55 will be attached with 56, then 54 will be deleted. So this is the final structure of delete with single node. So now we will discuss about deleting a node that has two children. So in case two children is there, means we have to delete the particular node means it will change the structure because it's how both two child, maybe the left subtree and right subtree may be there. So for that reason, we have to find the in-order traversal. From in-order traversal, predecessor and successor is there. So the predecessor will be given as longest or largest value in the left subtree, or successor will give smallest value in the right subtree. So we will see this in the diagrammatic representation. In the first diagram, I want to delete 56. The 56 have two child is there. like one is left subtree, another is right subtree. So if we are deleting this node, we have to replace this node. How we can delete this replace of the particular node, that we will discuss now. So one procedure is we can find largest value of left subtree, or second way we have to find minimum value of right subtree, because it is the predecessor of in-order traversal. It is successor of in-order traversal. So when we are finding the in-order traversal, so 56 in-order traversal, first we will go to left side, then root, then right it will come. When we are doing the in-order traversal 54, then it have another node. So what is the node? 55. So 54, 55, then 56, 78 it will come. So 55 is predecessor, 78 is successor. So we can change with predecessor or successor, anyone. So this diagram, we will check with predecessor value. So first we have to find which is the longest value of left subtree. So for that reason, it will apply. When we are going with 56, it will identify largest value is 55. Then 55 will be replaced with the particular node first. Then it is replaced by 55. Then finally we can remove 55. So it is changes the structure of the tree, but it's not affect the properties of the tree, as well as it is not lost any node in the particular tree. So it is predecessor method. How to successor methods? In order traversal 54, 55, 56, 78 it will come of the particular node in order traversal. So we will find smallest element in the right subtree. In the right subtree, smallest element is 78. So here the 78 will be replaced by the 56. So here 78 is replaced with the 56, and then the child 80 will be replaced with 78. Finally 80 will be removed from the tree. So this is the successor method. Any one of the method we can follow or delete a node which have two children. This is algorithm for deletion operations. First we have to check tree is null. That means there is no root node or tree is null. Then we can find value not found in the tree. Then in case it is not null, it will check with lesser than the tree data or greater than the tree data. If it is lesser than the data, it will go to find the where the value is present, that is tree left. It will apply the entire procedure recursively to find the particular value in the left side. In case it is greater, it will go to right side and find the particular value is present in the right side. So these two steps only finding the values are present in the left or right. If once it is found, then we will go to find the left subtree. So in case the values are there, we will go with predecessor method. Then in that method, we have to find longest value of the left subtree. So the largest value in the left subtree will be replaced with the data. So initially it will set temporary variable for store the largest value. That value assigned to the tree data, and then the tree pointer and particular temporary data will be removed. So initially temp equal to 3, else in case this condition is fails, we will go with right side data. So here both tree left and tree rights are null, means the tree equal to null. So finally it will set null. So tree left will be null, as well as we can check how the left side process happened. In case it is a root node, so we can check the root node have left subtree is null, right subtree is null. So if both are null means we can assign null value for the tree. So because we can delete the tree value also, we can delete root also. Else we can check it is left side is not equal to null means we can assign left pointer to the tree. So in case left child is there means the left child will be assigned as the root node will be deleted. In case it is the right child is there means the right child will be assigned as the root node, then right child will be removed. So finally, the element will be removed from the tree. So this is the procedure for deletion of the node. Now we are in end of the lecture. We have discussed about binary search tree and its operations. Now you should be able to explain the binary search tree and its operations. Here, multiple choice questions are given for understanding. Binary search tree is a binary tree but not ordered. A ordered binary tree. A binary tree. Not a binary tree but it is ordered. So the answer is it is a ordered binary tree. Second question, how to form a binary search tree? The left subtree is lesser than the root value, right subtree is greater than that root value. So the third option is correct for binary search tree. The third question, how search an element in the binary search tree. So first we know we have to apply the search operation. Then we can decide we will go for left or right side. The fourth operation is correct. Then fourth question, in binary search tree, if a node have no children, then be unable to delete the node, true or false. So if the node have no children, we can delete the node. So it is false. Fifth question, tree tends to data that is root not equal to null and left pointer and right pointer are equal to null. So that means only root nodes are there. A tree is empty. It is not correct. A tree have only one node. It is correct because it's have only root value. So other options are wrong. Sample questions are given for understanding purpose. Write an algorithm for insert a node in the binary search tree. It is apply level questions. Explain with algorithm to delete 40 from the following diagram. In this diagram, how you can delete 40 from this diagram. So the 40 have two child, so you can apply third category of deletion. Thank you very much for listening.